Hello, this is Professor Iris Miano coming at you with Day 2, Math 2 video lecture. And here we are. We're going to try and cover elements of 4 different sections today. I have them broken up into pieces, and the first section we're going to cover is on functions. So a function is a relation that maps each element of the inputs with exactly one element of the outputs. So there are two groups here to be considered, the inputs and outputs, and they are formally known as the domain and the range as defined here. So if x is an element of the inputs and y is an element of the outputs, then we would say that each element in the inputs or in the domain maps to exactly one element in the range in order for it to be a function. So yes, please go ahead and make sure you familiarize yourself with these terms. And also with function notation here, this particular one that I have highlighting over under my cursor, f of x is the way you would read this. And that's just saying that this is the function's value at x, is a way to say that. Okay, so again, the definition of a function is to say that as far as determining if a relation is a function, and that's what these first few exercises is going to be entailing, we want to see how we can determine that visually or with a set of ordered pairs. And then we'll get into another section later where we'll have another test for determining if relations are functions graphically. But for now, let's just go ahead and look at these two different visualizations. For numbers 1 and 2, we have two different columns of groups of elements, right? So there's, for number 1, we have this gas station and price per gallon sets of inputs and outputs respectively, the inputs being in green, the outputs being in this kind of coral pink color, and the arrows going across are the relation itself. That's the mapping of going from input to output. So that means that the input of Shell gas station has an output of $2.89 price per gallon. So notice that there are two inputs that are mapping to the same output. Is that okay in order for this relation to be a function? Yes, it is. And I like to liken this with an analogy, let me use proper English here, in which for a function, for a relation to be categorized as a function, it's kind of like you and your friend meeting up at the same coffee place, right? That's two inputs going to the same output, that's fine. Also, every input can go to a distinct place in the output. There doesn't need to be two meeting up at the same place, right? Everyone can be going to their own Starbucks or coffee place, as the case may be. However, so we would say, sorry, let me just get to the point here. This is indeed a function. Let me work on my handwriting. Yikes. So number 1 is definitely a function. We have no instance in which one input is being mapped to two separate outputs. Now, keeping that in mind, take a look at number 2 here. We have carrots as the input values and price as the outputs. Notice the input value of 0.17. It appears that it is being mapped to two separate places in the outputs, and that's to say that depending on what diamond carrots are associated with gradings for precious gems. Let's say it's diamonds that we're talking about here. A 0.71 carat diamond could have two different prices depending on where you're buying the diamond from, right? A person might appraise this 0.71 carat diamond as $1,575. Another appraiser might give it a little bit more of a boost, the $1,952. Okay, so I liken this to the coffee place analogy where it's like, oh, if I'm trying to go to two separate Starbucks at the same time, well, that doesn't make any sense as far as real life is concerned. So we would say that that is not a function. If you don't like my coffee meetup analogy, please throw it right in the garbage, okay? Essentially, what you need to be looking out for if you're trying to determine if a relation is a function is you're looking to see if any one input maps to two distinct outputs. If that ever happens, you do not have a function. It's still a relation. The relationship between the inputs and outputs is still considered a relation by definition, but it cannot be a function if if one input goes to two separate outputs. So let's do the same thing in order to test what's going on with numbers 3 and 4. And here we just have a list of ordered pairs. So you will want to notice if this is the relation that you're given, you want to scan your list of ordered pairs and see if the inputs, so that's your x values here of -4, -3, -2, -1, and then -4. If any of the inputs appear twice in this list of elements, that's what you want to look for. So, right? This is saying that -4 maps to 4 and it maps to 0 at the same time. That would be like my analogy of trying to go to two separate coffee shops at the same time. That is an instance of not having a function. So I'll go ahead and circle these outputs and say that this is not a function since -4 maps to both 4 and 0 at the same time. Remember, you can have two separate inputs mapped to the same output. That's kind of like meeting your friend at a coffee place, right? And so look at what's happening in example number 4. We have scan your inputs first. We have -2, 0, -1, and 4. Okay, this looks good. We only have distinct inputs, and they are going to the possible outputs are 16, 3, and 4. Notice that 4 is repeated, but that's fine. You just have -1 and 1 meeting up at the same coffee place. Again, I like this analogy because it works for me. It makes sense in my brain. If you don't like it, please don't worry about trying to make sense of it. I just think it's a good way to think about whether a relation is a function. So this is definitely a function. Function. Lord, I need to work on my handwriting. We have no instance of a single input mapping to two different outputs. Cool. So hopefully that makes sense, and if it doesn't, please ask in class. Okay. Next, we want to determine whether the equation defines y as a function of x. Cool. So if you have familiarity with these particular relations graphically, that's always nice. Here we have a absolute value equation, which graphically I'll just kind of draw a quick pic. We have x and y. It kind of looks like this, right? So here, oh, and let me go ahead and draw the trajectory in another color just to make it kind of pop. It looks more or less like a V shape. Okay, so we'll talk a little bit more about the vertical line test when we get into, I believe it's section, I forget if it's 1.2 or 2.1. We'll get to it in a little bit. But you will find that there is no instance in which the vertical line test is violated here, like there's no whatever. I'll get into that a little bit later on. What you want to focus on is there any instance in which you can plug in a value for x in which you would expect to get two separate values for y? Well, no. Whatever you plug in for x, there's only going to be one output. It's always going to be forced positive since it's the absolute value function that's being imposed on the x. However, you could have two separate x values that map to the same output. Like for instance, if x is -2 or if x is +2, the output mapping is going to be going to +2 no matter what. So we would say, yes, this is a function. Function. Always a single output. For each input. Okay, so that'll do it for number 5. In general, with these types of problems where you're given an equation and you want to determine whether the equation defines y as a function of x, if it's not already solved for y, you want to make sure you do it. Now for number 5 that we just went over and number 6 that we're going to talk about now, these equations are already solved for y. So you can just go straight to asking yourself, is there any instance when that I could put in a single value for x and I am going to get 2 separate values for y? And yes, that is definitely going to be the case for number 6 here. Okay, pretty much no matter what value you put in, you're going to get 2 outputs, right? Except for the only time that that wouldn't be the case is when you have x equaling 1/2. That'll make the radical a 0, and there's no such thing as plus or minus 0. 0 has no sign, so that would just be, I will say this is the only instance or only input that has a single output. Otherwise, you get 2 real outputs for every input, or 2 imaginary outputs, which is something that we'll get into in much more detail later. So I'll say otherwise there are 2 outputs for every input, therefore not a function. Notice that in number 7, we are not given the equation solved for y, so we need to solve this equation for y, and in doing so, we need to take the square root of both sides. So let me go ahead and show you how that works algebraically. So here's the original problem, right? Take the square root of both sides, and you need to do the plus or minus, right, square root on this side. In the event that the square root taking cancels with the squaring, like if that's what the whole purpose of this is, as far as you're taking the square root of both sides, then those are going to cancel out and you'll just be left with y. So essentially what's happening here is you have y equals plus or minus the square root of x. For the same reasons as you saw for number 6, this is going to be having lots of instances, and it only takes the once, but it's going to have many instances in which you will have 2 outputs for nearly every input. And that is a violation according to the definition of a function, so we will say not a function. And you can use the same reasoning as number 6. No need to invent the wheel, reinvent the wheel, that is. Okay, moving on. Let's go ahead and state the domain and the range, or sorry, just the domain. It's the only thing that we're going to focus on for now. Oops, excuse me. For numbers 8 and 9, and then that'll be it for our initial discussion on functions. We're going to revisit some of these elements later on in this very lecture. Okay, so notice the function f of x is equal to x squared plus 2. So hopefully you've had a little bit of a taste of function notation before coming into this class. Just so you know, x is the input value. It's generic before you have a specific value to put in. X is just a placeholder for some element of the domain. And so when you're asked to find the domain of the function, you're really looking for values that should not be plugged in to the function, like if it violates it in some way, as far as in the key types of functions that have domain restrictions is going to be rational functions. So look at number 9, hint, hint, that's a rational function, so we will have a domain restriction there. Or radical functions are the main ones. There are others, but those are the main ones to look for as in this initial bit. Notice that f of x in number 8 is a quadratic function, and quadratic functions have a domain always of all real numbers. And the way that you state this is using a set notation. So you use your curly bracket. Oh Lord, let me try that one more time. Oh, nope. Third time's the charm, huh? Love it. Okay, there we go. That's a curly bracket that I'll keep. You want to express the set, if you're trying to find the domain, it's the set of x such that, that's this vertical line, x is, you could say, an element of the real number set. So that's a little bit of mathematical shorthand. I'll just say that this translates as x is an element of the real number set. Otherwise, you might be trying to say what x can't be. If there are domain restrictions, that is what gets stated specifically in the domain, and then it's otherwise understood that any other real number besides what's specifically stated could be an element in the domain. Moving on to number 9 now, in order to address this formally. Please notice that we have a rational equation, or a rational function. So that means you set the denominator equal to 0, and whichever values you get from that, those are going to be the values that the domain is not allowed to have, because the denominator being equal to 0 makes for an undefined rational expression. So the rational function set denominator equal to 0. So that'll be x squared minus 16 equals 0, and then solve this equation, and that'll tell you which x values you have to exclude from your domain. So that'll be x squared equals 16. Square root both sides, we get x equals plus or minus 4. Oops, sorry. Let me get rid of that symbol. Plus or minus 4. There we go. So that means, as far as the domain set notation statement is concerned, curly bracket, the domain is x such that x cannot equal negative 4, comma 4. You just kind of list all of the elements that it can't be, and then it is generally understood that x can be otherwise any real number. Okay, so they're stating some domains. Let's switch gears. We are going to enter into elements of another section called F.3. So this is a preliminary section in your textbook. So it's before chapter 1 technically, and it concerns lines. So the first thing that I want to do is write for you, and if you're following along with me writing notes, I want you to write down as a little bit of review, the formulas for the following forms of a line or formulas. Okay, so here we go, starting with slope. Slope is generally called your m value, right? Your the variable associated with slope is usually m, and the way that you'll calculate it is to take the change in the y values. So y2 minus y1 over x2 minus x1. Let me erase that. That doesn't look very good as a subtraction symbol. x1, where x1 comma y1 and x2 comma y2 are given. So these are like the ordered pairs, let's say, that lie on a line, and you want to calculate the slope on the line that goes through those 2 points. You plug them into this formula, and there you go. And again, you already know this, but let me just specify that this is the rise, right, just a change in y, and then down here is the run, the change in x. Cool, so we'll definitely use that. Equation of a vertical line. Vertical lines always come in the form of x equals a, where a is some real number. A is an element in the real number set, so I'll just kind of specify that there with this little bit of mathematical shorthand. So this funky looking e, it's actually I think it's Greek, and it's just shorthand for is an element of, and then this fancy r is the mathematical shorthand for the real number set. Hopefully that's familiar to you guys, and if it's not, well, you've learned it from me. Cool. So all vertical lines come in the form of x equals some number. Horizontal lines, on the other hand, come in the form of y equals some number, some real number. Okay. Point slope form of the equation of the line is as follows. We have y minus y1 equals m times the quantity x minus x1, where m is your slope, and the point, right, is x1, y1 is a point on the line. Cool. Furthermore, slope-intercept form of an equation of a line, we have y equals mx plus b. Super familiar, I'm sure, to all of you. M, of course, is still slope. Boop-a-doop-doo. Hold on. Let me erase that. Slope. And b is the y-intercept. Technically, it's the y-value of your y-intercept. If you want the y-intercept as an ordered pair, it would be 0, comma b. The general standard form of an equation of a line is ax plus by equals c, where a, b, and c are any real numbers. Generally, they are usually integers, and a is furthermore usually positive, but that doesn't have to be the case. According to the definition in the textbook, they are just all real numbers. So that's meant to be a fancy R. Cool, cool, cool. Okay, moving right along. Parallel lines have, what's the relationship between slopes of parallel lines? I'm sure you all have ever heard this. They have equal slopes, so I'll just kind of fill in the blank there. Well, perpendicular lines have, there's two separate blanks here because there are two different describers for the relationship between the slopes of perpendicular lines, and they are opposite reciprocals. Opposite reciprocal. I don't mean to pluralize that. Let me go ahead and erase that. Yeah. So yes, you have to have both of those things in order to be perpendicular line slopes. You have to be opposite one another and the flip, which is the reciprocal. All right, so we'll talk about that again in a little bit. Just moving right along to the next example. I want to get some plotting in with you guys. Here we go. Let's go ahead and plot the pair of points and determine the slope of the line that connects them. Oh, wait a second. There is no pair of points. Let me just go ahead and make up another point here. My bad. Let's see. Oh wait, or do I have one? Is it just behind? Nope, it's not behind this. Hold up, y'all. I just made that up. Okay, now let's go ahead and draw. We'll change the color up for funsies. Let's go with this purple bit. Okay, and so we're going to plot -2, 3. So here's a little bit of review on how to plot. Start with the x value, start at the origin, go back 2 spots to go -2 in the x direction, and then +3. That's going to have you right there. The sloppy point right there. And then 3, -1 is going to be out 1, 2, 3, and then down 1. Okay, great. Determine the slope of the line that connects them. So if I want to determine the slope, I'm going to count the rise, okay, from one point to another. Maybe I'll start with this point so I have a positive rise. So how much rise do I have? Well, so that's this kind of bit right here. This is the rise. And how many units is that? 1, 2, 3, 4. So a rise of +4. But then from here, I have to run in the negative direction. So this is a run of 1, 2, 3, 4, 5. So that's a -5 run. So the slope, which is the rise over run, is going to be, again, the rise was a 4, the run was a -5, so really it's a -4/5 slope. I know what you must be thinking. Is it okay if I keep the negative sign in the denominator? I mean, I guess so. When you type in answers such as this into perhaps the homework of the online homework, they're probably going to want you to have the negative sign out in front of the fraction because that is the most simplified and aesthetically pleasing version of this negative fraction. Okay, cool, cool, cool. But yeah, all right, here's another example. We are given different pieces of information and we are asked to do something different. We want to graph the line that contains the point P and has slope M. Okay, find the point slope form of the equation of the line. We will do that. Let's start by plotting the first point of 1, 3. So that's 1 in the x direction, 3 up in the y direction. That's the ordered pair 1, 3 right here. 1, 3. Okay, and we're going to use the slope of -1/4 in order to plot an additional point. So from 1, 3, go ahead and go, if you want, you can either go down 1 and 4 units to the right to get an additional point, or you can go up 1, but then you have to go 4 units to the 1, 2, 3, 4 to the left to indicate negative movement in the x direction. It doesn't matter which one you do. As you can see, plotting both of those additional points has you lying on the same line. So I'm going to go ahead and insert a line proper just so I have a straight trajectory here. And I'm going to have it go through all of my points to the best of my ability. Let me just do some slight adjustments to get it going. Yeah, that looks pretty good. I'm also going to make my line the color that goes with this and make it a little bit thicker, just so it looks real pretty. Cool, I like that. Look at that, beautiful. Okay, so I've graphed my line, check that off the list, and then find the point slope form of the equation. Okay, that's easy. I just plug in my point and my slope, right, into this equation. Y minus y1. Oh, sorry. Draw. Let's erase this a little bit. Equals m times the quantity x minus x1. So literally just plug in your x1, y1, and your m. Y minus 3 equals -1/4 times x minus 3. Or sorry, 1. That's right. Okay, and that's it for that one. Boom. And box it up. Fantastic. Moving on. Find an equation for line L. Here we go. Line L is this downward sloping line. And how do I know it's downward sloping? Because as I scan the graphic from left to right, the trajectory of line L, as it's labeled here, is moving downward. Okay, so line L happens to be, oh, you know what? I don't have it written here. Hopefully it is abundantly clear that line L is perpendicular to the other line, the unlabeled line. And so you can glean from that it should have the opposite reciprocal slope. You can either surmise that from the picture, or you could just go ahead and say, all right, I know that the slope has to be what is it, -1/2, because we have from one point to another. Hopefully you can see my cursor here. Like let's say we're starting at this point. I go down 1 unit and then 2 units to the right. So that's a -1 rise and a +2 run. That's -1/2 as the slope. And then we also have this point of 1, 2. So I could put all that information together. I'll go ahead and say I can see that the slope is m -1/2. And then I also have a point that I know lies on this line of 1, 2. So I can use the point slope form. To come up with this equation of the line. Now the equation was never specified to have a certain form, so I could just leave it at this. Now if for some reason I wanted to have this equation specifically be a point or a slope-intercept form rather, then I would need to distribute through this -1/2 and solve for y essentially. So I'll go ahead and demonstrate that real quick just to you know, show you what's up with that. Let's add 2 to both sides, and that would give me y equals -1/2 x plus 5/2, or you can call it 2.5. So I'll call it 5/2. Sweet. Yeah, and so that'll give you the equation of line L there in a form of my choosing. I chose to come up with the slope-intercept form, but I was not forced to do so. Okay, cool, cool, cool. All right, we have just 2 more sections to cover. This next one, 1.2, is basically the main thing we want to glean from this is how to use the vertical line test to determine if the graph of a relation is indeed a function. So notice for problems 13 through 24, and I just took this straight out of your textbook, I have several different graphs, and they're all relations. We want to determine the domain and range, intercepts if any, symmetry with respect to the x-axis, y-axis, or origin. So I'm just going to describe these very quickly so that we don't spend too much time talking about this stuff. I don't think we need to spend a lot of time. Notice that off to the side I have my red vertical line here, and that's because the vertical line test states, and I'll just read this for you, it's a graphical relation is a function. Now I don't have a typo here, it looks like one, but this IFF word is mathematical shorthand for the phrase if and only if. So the vertical line test reads as a graphical representation is a function if and only if every possible vertical line passes through it no more than once. Okay, so here is a vertical line, and I'm going to use this to kind of slide it over my graph to see if there's any instance in which the blue crosses the red more than once. Look what's happening with number 13. Notice that if I have my vertical line just right here, over this little edge of my curved trajectories, it only seems to be crossing once, but if I move it any further to the right, I have 2 crossings. You guys see that? Here's a crossing right here, and here's another crossing right here on the same vertical line. So that makes this not a function, okay? Not a function, so no to the function. The domain and range, I'll just go ahead and say those out loud for each one as I go. The domain is going to be all numbers except for everything in between -1 and 1. That's going to be a no-go here. The range appears to go in, off into infinity in both directions, so the range is all real numbers. Moving on to 14, is that a function? Let's use my vertical line test. Yep. All throughout, that blue line only crossed the red line once, so it is, yes, a function. Oh, sorry, I didn't talk about intercepts here. There are no y-intercepts. There are x-intercepts at -1 and 1, and there is symmetry according to the y-axis and the x-axis. If you want to know about symmetry, imagine yourself folding the coordinate plane across the x or the y axis, and if the trajectories line up on top of each other, then it does have that symmetry. Okay, we do not have any symmetry for number 14. We have a y-intercept at +1 and no x-intercept. This blue line going off and seemingly riding the x-axis means that it shouldn't cross anywhere later on. Okay, moving on to 15. it looks like we are passing the vertical line test. Did you see how I did that sweep and it did not cross more than once? So it's yes, a function. We have here y-intercept at 1, x-intercepts at positive and negative pi over 2. We have symmetry over the y-axis, because if you were to fold it in half on the y-axis, it would the trajectories would lay on top of each other. For 16, we are passing the vertical line test, y'all, so that's yes, a function. We have, it looks like rotational symmetry over the origin. If you were to rotate what's happening in quadrant 3 by 180 degrees, you would exactly line up with quadrant 1's trajectory. If I'm going too fast on this, we could talk more about it a little bit later. What are the x and y intercepts? Well, x and y have an intercept at the origin. It's definitely crossing right here. And then there are otherwise x-intercepts at positive and negative pi. Moving on to 16. It looks like, ooh, check this out. Right there, boom. There's an instance in which I am not passing the vertical line test, so that is not a function. We seem to have symmetry over the x-axis, y-intercept and an x-intercept at the origin, and that is it. Okay, moving on. Oh, look at that. Not a function. Nope. X and y intercepts happening at positive 2 and negative 2 for both x and y axes respectively, and we have rotational symmetry, x-axis symmetry and y-axis symmetry. This number 19 is indeed a function, so yes there. No symmetry. We have an x-intercept at 1. All right. Looks like we are passing the vertical line test, so the number 20 is a function. No symmetry, x and y intercept at the origin. Moving on to number 21. Look at that. Yes, a function. X intercepts at positive and negative 3, y intercept at 2. Function passing there for number 22. And you guys, I think, get the picture about x and y intercepts. Oh, sorry, this one has a symmetry on the y-axis. Going here, I see no symmetries. X intercepts at negative 3 and positive 2, y-intercept at 2. This one appears to be passing the vertical line test, no problem. That's a yes here. And a yes here. No problems there. No symmetry on 23, x-intercepts at 1 and 3, y-intercept at 9 for number 23, that is. For number 24, we have a y-intercept at 4, an x-intercept at 2, and no symmetries. Cool. So hopefully that was sufficient for showing what to do there. We have one last example concerning supply and demand. It's a little bit of a word problem with linear functions. That's what 2.1 is all about. So we have a supply function and a demand function, which is a function of the price of some t-shirts at a concert. Remember concerts? Yeah. So someday maybe we'll be able to go to concerts again. In any event, let's talk about the supply and demand set of linear functions. P is the price of the t-shirt. We want to A, find the equilibrium price for t-shirts at this concert. What is the equilibrium quantity? In order to find equilibrium, you simply set supply functions equal to demand functions. Okay, so this is for part A. So that'll be having negative 600, P, oh, excuse me, not P, negative 600 alone, plus 50p equal to 1200 minus 25p, and you're going to solve for p, getting p all by itself, you're going to use properties of equality, and I believe you will get p equals 24. So that means that the equilibrium price here is $24. And what is the equilibrium quantity? Well, that'll be either supply or demand. It doesn't matter because they're equal to each other. It's like, what is S of 24? and I believe that'll be 600 t-shirts. So you plug that in and you'll find that that is the case. If you want me to work this out in lecture, that's perfectly fine. So it says determine the prices for which quantity demanded is greater than quantity supplied. So supplied quantity is S of P, demand quantity is D of P. So basically you just have to create an inequality for part B here. So quantity demanded, that's this, needs to be greater than, strictly greater than quantity supplied. So then you plug in these elements, right? That'll be 1200 minus 25p is less than negative 600 plus 50p. So you'll solve this inequality and you'll find that p is less than, strictly less than 24. That 24 shows up again as we would expect. But you have to keep in mind that the price, because of the context of the problem, the price cannot be less than 0. It can be equal to 0 technically, although that'd be giving away the t-shirts and that's not very conducive to business, but I guess technically it could be a 0. So this would be the range of prices when demand, quantity demanded is greater than quantity supplied. Now C, this last question, is more of a qualitative question than anything else. It asks, what do you think will eventually happen to the price of t-shirts if quantity demanded is greater than quantity supplied? Well, think about that, and think about that in the simplest terms possible. Like, let's say you're at a concert that you would really want to go to. Personally, I would like to go back in time and go to a Talking Heads concert. And let's say you're trying to buy a t-shirt, and let's say there was only one t-shirt left and there were two of you that wanted to buy it. Well, then there might be a bidding war, that develops here. And so in that case, in the scenario, you might expect that the price of the t-shirt would increase. So that's going to be my official answer here. The price would probably increase. That's all I have to say about these sections for day 2 lecture. Let's go ahead and when we're all ready, reconvene for discussion. Thank you all so much.